I'm Norman Waldberger. This is a course in universal hyperbolic geometry, a new and improved version of the subject which relies on an algebraic approach and doesn't involve any transcendental functions. We're working over the rational numbers, and we've established in the last few videos the four main laws of trigonometry in the subject. So we're talking about a triangle in the hyperbolic plane, 3 points A1, A2, A3, with three quadrances, Q1, Q2, Q3, and three spreads, S1, S2, and S3. And the four main laws, just to review, are first of all Pythagoras' theorem, that if one of these spreads is 1, in other words, if we have a right triangle where two sides are perpendicular, say if S3 is equal to 1, that would mean that these two sides are perpendicular, then Q3 equals Q1 plus Q2 minus the product of Q1 and Q2. The triple quad formula is another special case when in fact all 3 points are collinear. So when this point collapses so that it's on the line, which is another way of saying that the spread S3 is 0. So in that case, the relationship between the three quadrances is this one here, which is the same as the triple spread formula in Euclidean rational trigonometry. Then we have the spread law, that the ratios of spreads to opposite quadrances is the same at all three vertices. And finally, the cross law involving the three quadrances, Q1, Q2, Q3, and the spread S3. That thing squared is 4, 1 minus Q1, 1 minus Q2, 1 minus Q3. Now later on we'll see that all of these laws have dual formulations where the quadrances and the spreads are interchanged. In fact, it's not hard to imagine what those duals would be, but we will have a separate video on the duals. Today we're going to look at one of first of a series of applications of these laws. We're going to look at basically right triangles and a very important result called Thales' theorem and another important result called Napier's rules having to do with the relationships in a right triangle in hyperbolic geometry. First, let's make sure we understand exactly what a right triangle is. So a triangle A1, A2, A3 is called a right triangle precisely when at least one of its spreads equals 1. Now a spread between two lines equals 1. That's exactly what we mean by those two lines being perpendicular. So we're talking about a triangle so that at least two of its sides are perpendicular. Now in ordinary Euclidean geometry, a triangle can only have one right angle. There can be only two of its sides which are perpendicular. However, in hyperbolic geometry, the situation is richer. We can have a triangle which is singly right, with just one vertex where perpendicular lines meet, or doubly right, where there are two vertices with perpendicular lines meeting there, or triply right, in fact, where all three vertices have perpendicular lines meeting there. So here's an example of the singly right triangle. I remind you that what that means geometrically is if you take, say, this line here and you look at its dual, then any line through that dual, say that one there, will be perpendicular to the line we start with. So any one of these lines is perpendicular to that one. That's what perpendicularity amounts to in this hyperbolic projective setting. So that's an example of a triangle which is singly right. There's just one perpendicular vertex there. Here we have a doubly right triangle where the dual of this line is this point here, and both of these sides of the triangle go through the dual point. So that's going to be perpendicular, and that's going to be perpendicular. In fact, any line through here will be perpendicular to this one. So these are just two particular lines that are perpendicular to this side. So here's an example of a triply right triangle. which we talked already quite a lot about. Let me just remind you that you get that by choosing 4 points on the null circle, and then joining those 4 points with 6 possible lines. And those 6 possible lines are paired into 3 pairs. So that pair, and that pair. Each one of those pairs determines a point of intersection, and that's the diagonal triangle of the original null quadrangle. And that construction is exactly the construction of the dual of a line. So the dual of this line is exactly that point, the dual of this line is that point, the dual of this line is that point. So all these points are mutually perpendicular, and all 3 lines are mutually perpendicular too. So that's a triply right triangle. Alright, so that's what a right triangle is. Now let's have a look at Thales' theorem. So our standard convention, here in this diagram, we have a point A1, A2, A3 forming the triangle A1, A2, A3 with quadrants Q1 opposite A1, Q2 opposite A2, and Q3 opposite A3, and spreads S1 here, S2 here, and S3 here. Okay, so Thales' theorem says that if S3 is equal to 1, in other words, if these 2 lines are perpendicular, then S1 is Q1 over Q3, and S2 is Q2 over Q3. So in this diagram here, where we do in fact have perpendicular lines there, because this line goes through the dual of this one, or in fact, since this line goes through the dual of that one, same thing. Thales' theorem says that the spread at this vertex, S1 here, can be calculated by just taking the ratio of the opposite quadrants to what we might call the hypotenuse quadrants. Okay, so this is a little right triangle right here. There's the right angle, so to speak. Actually, the right spread would be better terminology. So this deserves to be called the hypotenuse quadrants. And from this point here, this is naturally to be thought of as the opposite quadrants. This one might be called the adjacent quadrants. Thales' theorem is saying that the spread S1 is the opposite quadrants divided by the hypotenuse quadrants. It's just a ratio of 2 quadrants. And exactly similarly, from the point of view at A2, we're interested in this spread S2. Then we also have another right triangle here. Now from this point of view, the opposite quadrants will be this one. The hypotenuse is still this. S2 is Q2 over Q3. This quadrants divided by this quadrants. The theorem is an immediate consequence of the spread law. There's the spread law. We're assuming that S3 is equal to 1. So if that's equal to 1, then S1 equals Q1 over Q3. And S2 equals Q2 over Q3. It's immediate consequence of the spread law. Nevertheless, it's a very important and fundamental result that you have to learn. One of its major implications is that there's a kind of similarity going on here in hyperbolic geometry. A similarity with respect to sort of right triangles. Now in classical hyperbolic geometry, this is not properly understood. Classical hyperbolic geometry, that antiquated kind of stuff that you learn in textbooks and at universities, that doesn't appreciate the importance of quadrants. In that classical hyperbolic geometry, people think that one should think about distance and angle as the fundamental notions. But the consequence is that in classical hyperbolic geometry, it's sort of well known that similarity plays no role. Similar triangles don't exist. Well, that's true to a certain extent, but what Thales' theorem is telling us is that there is a kind of similarity. And I want to explain that to you now. So here in this diagram, I've also, in addition, created another right triangle by choosing another line through the dual here. And this new triangle will have a vertex, we'll call it A2 prime at A3 prime. So the new triangle is going to be this bigger one right here. The spread here, S1, is still the same, but now the quadrants Q1 is replaced with Q1 prime here, and the quadrants Q3 is replaced by this quadrant's Q3 prime, which we denote like this. So Thales' theorem applies to this right triangle just as well as it does to this right triangle, and tells us that this spread S1 is also equal to Q1 prime divided by Q3 prime. So Q1 over Q3, the ratio of opposite to hypotenuse in the smaller triangle, is equal to Q1 prime over Q3 prime, the ratio of opposite over hypotenuse in the bigger triangle. So these two triangles are not similar, but they share this spread here. They're both right triangles, and so the ratios of these quadrants, opposite to hypotenuse, are equal. It's interesting. In classical hyperbolic geometry, where the quadrants is replaced with distance, and so to go from quadrants to distance, you have to do some transcendental things. You have to take a square root, and then you have to do a sort of an arc cinch function. So it's some kind of transcendental function. I'll talk about that in a future video. But then you end up with distance rather than quadrants. And for distance, this kind of relation doesn't work. It's not true that the ratio of this distance to this distance is equal to this distance divided by that distance. So in classical hyperbolic geometry, this result is a little bit obscured. And its importance is not properly recognized. It's a very important fact, in fact. This Thales theorem is also related to Euclidean rational trigonometry. And in fact, it sort of sheds some light on why the spread is a crucial ratio in Euclidean rational trigonometry. So in Euclidean geometry, so this is just a small diversion here just on this page. Let's suppose we're in the Euclidean situation here. Here's a triangle, and it's a right triangle. So these two lines are perpendicular in the usual sense. And notice that the points have capitals and the quadrants have capitals and the lines are small, alerting us to the fact that we're in the affine situation here, not in the projective situation. Now, in Euclidean rational trigonometry, and one of the very first things that you do, you have to define what is a spread. And there are various ways of doing that, but the simplest way is probably in terms of a ratio of two quadrants. So once you've defined the quadrants, which in Euclidean geometry is just the square of the distance, or rather the distance is the square root of the quadrants, the spread here between these two lines can be defined as the ratio between this opposite quadrants and this hypotenuse quadrants. And in Euclidean geometry, the fact that similar triangles exist makes that definition well defined. It doesn't matter which point we drop here. If we chose a bigger triangle, then this ratio of opposite to hypotenuse would be the same. That makes the spread well defined. Now, many people have asked me, okay, why do we use the spread? Why do we use this particular ratio between these three quadrants? And why not say the ratio of this to this, or maybe this to this, or some of the reciprocal ratios? So those other ratios do in fact have names in rational trigonometry, and they do play an interesting role, but it's a secondary role. The spread is the primary quantity, and the cross and the twist are secondary quantities. So what is the cross? The cross here okay, at this vertex, is Q2 over Q3. It's that ratio, adjacent over hypotenuse. And the twist is the ratio Q1 over Q2, opposite over adjacent. So now I can give you a kind of a sophisticated reason why the spread is in fact the primary quantity. It's because when we go to the projective setting, that is hyperbolic geometry, it's exactly the spread that is a well-defined concept between two lines. So here is now the hyperbolic setting. Here we have two lines, capital L2 and capital L3, and we're interested in defining some object or number between them. Okay, so what we have done, the spread that we've defined, is, we've seen now as a result of Thales' theorem, it's this quadrants, the opposite quadrants, divided by the hypotenuse quadrants. And that's now well defined. It doesn't matter which point we choose on this line and drop a perpendicular. We can choose any point on this line, drop a perpendicular, and then take opposite over hypotenuse. We'll always get the same number, just like we do in the Euclidean case. But that's not true for the ratios involved here in the cross or in the twist. So in other words, if you look in this same triangle here, the smaller one, and you look at the ratio of this quadrants to this quadrants, that ratio is different from the ratio of this bigger quadrants down here to this bigger quadrants on the hypotenuse. In other words, when we go from the smaller triangle to the bigger triangle, that ratio changes. And that's the same with the ratio of opposite over adjacent. So this quadrants divided by this quadrants is not equal to this quadrants divided by this quadrants. There is something special about exactly this ratio, this one to this one. That is the same in both triangles. It's a sophisticated but important explanation for why it's the spread which is the primary quantity between two lines. Thales' theorem has another interesting and important application that relates to the quadria of a triangle. This is the concept that we called script A, or calligraphic A. It was a number associated to a triangle. And I said, perhaps to you then, that the quadria is the single most important number associated to a triangle. If you only know one thing about a triangle, the best thing to know is what is its quadria. And we made a calculation that showed that these three quantities were all equal. So if you take Q1 times Q2 and you multiply by the spread S3, that's the same as Q1 times Q3 times the spread S2, and that's the same as Q2 times Q3 times the spread S1. Now we're going to do something a little bit new. We're going to introduce an altitude of this triangle. So we're going to drop a perpendicular, say from this point to the opposite line. And I remind you that geometrically, graphically, that simply means it's a line that goes through this point and the dual of this opposite line. So the dual is that point there. So to get an altitude in hyperbolic geometry is simpler than in Euclidean geometry. We just connect the dots. So there's an altitude, and it meets the base here at some new point, and we can talk about the quadrants between this A3 and this new point. Let's call it H3, because it's a kind of a height quadrants, and is associated to the vertex A sub 3. Now have a look in this triangle here. In this triangle here, which is now a right triangle, the spread S1 is, according to Thales' theorem, H3 divided by Q2. Right there, S1 equals H3 over Q2. So if we just clear the denominator, it means that H3 is equal to Q2 times S1. H3 equals Q2 times S1. Now, it follows that if we have a look back here at the equation for the quadria, say this one right here, Q2, Q3, S1, let's rewrite it as Q3 times Q2, S1. Then this Q2, S1 combination is exactly what we're calling H3. So the quadria can be rewritten as the product of the quadrants Q3 times the quadrants H3. The argument is exactly symmetrical, so we could have just as well done this with this sort of as the base, or with this as the base, considering the other two altitudes, call them H1 and H2, the quadrances. So we get that the quadria can be written either as Q1 times H1, so that quadrants times that quadrants, or as Q2 times H2, that quadrants times that perpendicular quadrants, or as Q3 times H3, as Q3 times H3. It's like base times height, except that we're not talking about distances, we're talking about quadrances. Which at least suggests in our mind that very roughly we should think of quadria as being somehow analogous to the square of the area. Well, maybe proportional to. We haven't defined the area of a hyperbolic triangle. Okay, but nevertheless, in the Euclidean case, it turns out that the quadria, which is not quite the same here, there's a factor of 4 difference, but it turns out to be exactly 16 times the square of the area. But anyway, just in your mind, I want you to remember that the quadria, which maybe seem a little bit artificial this way, has a very natural geometrical interpretation. It's just base quadrants times height quadrants. And beautifully, that doesn't depend on which side you start from. That base quadrants times that height quadrants is the same as that base quadrants times that height quadrants is the same as that base quadrants times that height quadrants. Okay, now it's time for Napier's rules. Now, Napier was a 17th century mathematician involved in logarithms and other things, but his name has been associated to some rules which got incorporated into hyperbolic geometry in classical form. Now, the rules that we're giving here are quite different in form to the Napier's rules that you find in hyperbolic geometry texts. So if you're a proponent of classical hyperbolic geometry, you should have a very good look at comparing the Napier's rules that you find in your textbooks with the Napier's rules that I'm presenting here. Right. The ones I'm presenting here are far superior. There's just no reasonable objection, I think, to that statement possible. So, what are these rules? Well, the idea is that if we have a right triangle, like this one, then one of the spreads we know. It means that that spread is equal to 1. So the trigonometry of this triangle has 5 unknown quantities. There are the 3 quadrances, Q1, Q2, and Q3, and the other 2 spreads, S1 and S2. Napier's rule says that if we have a right triangle, and here are the quadrances, and here are the spreads, and we suppose that S3 is the spread that's equal to 1, then any 2 of these 5 numbers determine the other 3. And they do so in a very simple way, only by using these 3 basic equations. And these 3 basic equations are the Thales rules for the spread S1 and the spread S2, and Pythagoras' theorem, the relation between the 3 quadrances. So the claim is that just using these 3 equations, you can solve for all 5 of these if you're given any 2 of them. The proof requires only high school algebra. So it's a purely algebraic exercise that you could give a high school class. You could say, ladies and gentlemen, here are 3 equations. Now suppose that I give you Q2 and S1. Solve for the other three variables. You don't have to know what these variables mean. You don't need to know any geometry. You don't need to know this has any connection with hyperbolic geometry. It's an exercise in high school algebra. And it's a very interesting exercise, as we'll see. So maybe a good opportunity here for you, if you like a little bit of practice with algebra. Stop the video, get out your pencils, pens, and papers, and work this all out. Okay? So work out all the different possible cases, any two of them. How do you get the other three? And you'll get equations for the other three variables starting from the two known variables. So have a go. Now I'll show you how it works. Alright, so let's go through this case by case. The first case we're going to look at is when two of the three quadrances are known. So two of these three are known. How do you find the other quantities? Well, the relationship between the three quadrances is given by Pythagoras' theorem. And this is linear in each of the three variables. So if we want to solve for Q1, we just factor the Q1 terms together, bring everything else to the other side. We get Q3 minus Q2 divided by 1 minus Q2. And symmetrically, Q2 equals Q3 minus Q1 divided by 1 minus Q1. So if any two of these are known, we can solve for the third one by one of these equations. We'll use this one if we need to find Q3. We'll use this one if we need to find Q1. We'll use this one if we need to find Q2. So after we've done that, now we have all three quadrances. Well, then immediately Thales' two rules give us the two spreads. S1 is Q1 over Q3. S2 is Q2 over Q3. So we're finished. Well, we're finished with case 1 if we start with two quadrances known. Case 2. Suppose that the two spreads are known. S1 and S2 are known. Well, we can write these Thales rules this way. We can write this as Q1 equals Q3 times S1, and this one as Q2 equals Q3 times S2. And then we can plug these values into Pythagoras. So here's Pythagoras. So we would get Q3 equals Q3 times S1 plus Q3 times S2 minus the product of these two would be Q3 squared times S1, S2. Now there's a common factor of Q3 in all of those terms. So let's get rid of it. Let's just cancel it out. Then we're left with 1 on the left-hand side equals just S1 because we've canceled the Q3 plus S2 because we've canceled this Q3 minus S1, S2, Q3 because we've canceled one of the Q3s that gets multiplied together. And now we look at this and say, aha, well, here's now an equation for Q3. We can solve Q3 in terms of S1 and S2. Just bring that to this side, bring the 1 to this side. Q3 equals S1 plus S2 minus 1 all over the product S1, S2. And once we have Q3, well, then we can find Q1 by just multiplying it by S1. So if we multiply this by S1, well, the S1 in the denominator just disappears, and we have S1 plus S2 minus 1 divided by S2. And if we want to find Q2, then we multiply this by S2. Now the S2 in the denominator disappears. We get S1 plus S2 minus 1 divided by S1. That's case 2 finished. Now the other cases are when we know one quadrant and one spread. But there are essentially 3 different cases that we need to look at there. Because if we know one spread, it doesn't really matter which one we choose because S1 and S2 are symmetrical. But once we've chosen, say, that we know S1, then Q1, Q2, Q3, they're all different as far as S1 is concerned. So there's 3 cases to look at there. Okay, so let's look at these last three cases. So the case 3 is, let's say we know the spread S1 and the quadrants Q3. We have to find the other three quantities, namely Q1, Q2, and S2. So how do we do that? Well, first of all, Q1 equals Q3 times S1. That's just Thales' law, S1 equals Q1 over Q3, rewritten. But since we know S1 and Q3, well, immediately now we know what Q1 is. What about Q2? Well, here's an expression for Q2 in terms of Q3 and Q1. Where does that come from? Well, that was Pythagoras' theorem rewritten. If you look on the previous slide, when we started with Pythagoras' theorem, we saw we could rewrite that solving for either Q2 or Q1. And here's what Q2 was in terms of Q1 and Q3. Well, we've just figured out what Q1 is. It's Q3 times S1, so let's plug that in. So we replace this one with Q3 S1. So then the numerator is Q3 times 1 minus S1, and the denominator 1 minus Q3 times S1. And now S2 is, according to Thales' theorem, the other Thales theorem, Q2 over Q3. We've just figured out what Q2 is. So we need to divide this by Q3, and conveniently that factor there will just disappear. We'll have 1 minus S1 over 1 minus Q3 times S1. That's that case disposed of. Now the case when S1 and Q1 are known. Alright, so here's again Thales' result, a little bit rewritten, now showing that we can find Q3 in terms of Q1 and S1. So Q3 is known. Here's that same formula for Q2, and now we're going to replace the Q3 with Q1 over S1. Well, what happens, there's a fraction there, Q1 over S1. So what we want to do is we want to multiply top and bottom by the denominator S1. So that will clear that fraction. It will be Q1 and minus Q1 times S1. And then when we multiply this by S1, well, we just get an S1 multiplying. Right, so that's two steps. First step is to replace Q3 with Q1 over S1. And the second step, simplified by multiplying top and bottom by S1 to get rid of that denominator there. And then finally, S2, which is Q2 over Q3, is the ratio between this quantity and this quantity. So if we take this and divide it by this, so we're taking this and dividing by this, well, that Q1 and S1 that's there will just be divided out by Q1 S1 there. So the result will just be 1 minus S1 over 1 minus Q1. And finally, the last case, when S1 and Q2 are known. Okay, so there's Q1 equals Q3 S1, the same thing that we're using there and there. We're going to now plug that into Pythagoras. So there's Q3 equals Q1, replace there, plus Q2 minus the product between Q1 and Q2. So there's Q2 and there's Q1. But having done that, we now see that the Q3 is appearing right there, right there, right there, and the other two quantities are the ones that we already know. So the Q3, if we bring that all to one side, there's going to be only Q2 left on the right-hand side, and then on this side there will be a Q3 times 1 minus S1 plus Q2 times S1. So then we'll divide by that. Divide by 1 minus S1 plus S1 Q2, and I've just rewritten it a little bit like that. So that's what Q3 is. Then Q1 is Q3 times S1. So it means we just take this and multiply by S1. And then S2 is, by Thales' theorem, Q2 over Q3. Well, Q2 we already know. Q3 is right there. So if we divide Q2 by this, well, then the Q2 appears in top and the bottom, and that's divided out. And just the reciprocal of this gives us 1 minus S1 times 1 minus Q2 on the top. That's the end of that case. And so that's the end of the proof. We don't individually have to go through the cases of S2 and the various quadrances, because they're exactly like this one, just with the 1s and 2s interchanged. Right? There's a basic symmetry between the points A1 and A2 in this right triangle. A3 is where the right spread is. So we've got all kinds of lovely formulas obtained here. And these formulas are very useful. Do I want you to memorize them? No, definitely not, because there's too many of them. I want you to remember that they can all be obtained from the three basic equations: the two Thales equations and Pythagoras' theorem. So in any situation where you need to apply Napier's rules, just remember the three basic equations and say, all right, I remember the basic idea, just basic high school algebra, a little bit of fiddling around will let us calculate the other three if we know any two. But please, especially if your algebra is not too strong, this is a great place to practice. So you can, for example, put this away and try to reconstruct this argument on your own. Derive the same results on your own. See if you get the same formulas that I have. Pythagoras' theorem, Thales' theorem, Napier's rules. They are three important tools to deal with right triangles. It means that whenever we have a right triangle appearing, we are confident that we can understand that situation completely. This leads to a general philosophy in the subject, that when in doubt, drop some perpendiculars to create some right triangles. If you don't know what else to do, that's probably not a bad place to start. By creating some right triangles, perhaps just by dropping perpendiculars, which you can always do, then you have some right triangles and you can apply these three powerful ideas or formulas: Pythagoras, Thales, and Napier's. So it's time for a few exercises here, and I'll give you some exercises that are perhaps of independent interest, and you can check some formulas and derive them yourself. So the first exercise concerns a right triangle. So we have a right triangle here, A1, A2, A3. You can see the little right there. These two sides are perpendicular at A3 as before. And now what we've done is we've dropped a perpendicular from the right vertex to the other side. And we've called that point F for foot of the altitude, and we'll say that that quadrant there is H. That automatically gives a few other quantities of interest. So besides the regular quadrants as Q1, Q2, Q3, and the regular spreads S1 and S2, we now have two additional quadrants, that one R1 and that one R2. And we have two additional spreads, that spread R1 and that spread R2. So the exercise is to come up with some formulas for H, R1, and R2, and capital R1 and capital R2 in terms of the quadrants Q1, Q2, and Q3, say. So show that H is Q1, Q2 over Q3. Show that R1 is given by this formula. Find a corresponding formula for R2. Show that capital R1 is given by this formula. Find a corresponding formula for R2. And say, look at the ratio capital R1 to R2, the ratio between these two. Show that's given by that expression. That's a reasonably common configuration. It's nice to have some control of the various quantities that are involved. Our second exercise deals with a triangle, A1, A2, A3, that has an additional property besides being a right triangle. It's also an isosceles triangle, by which we mean that this quadrants and this quadrants are equal. So what we're usually calling Q1 and Q2, well, they're both equal to, let's say, the number Q. And the two spreads, usually called S1 and S2, they're both equal to S. This third spread as 1, we're assuming it's still a right triangle. And let's call the hypotenuse quadrants R in this case. So you get to establish just some basic formulas that R is equal to Q times 2 minus Q, that S is 1 over 2 minus Q, or Q equals 2 minus 1 over S. And you can have a look at some special cases. So for example, if S happens to be the number 1 over N, like maybe 1/3 or 1/4, then you can find Q and R. And it's kind of interesting to maybe calculate a few special cases, and especially the case S equals 1/2. It's particularly interesting, sort of conundrum. What happens when N equals 2? What kind of triangle do you get? For our third exercise, suppose we have our triangle A1, A2, A3, which is a doubly right triangle. So that S1 equals S2 equals 1, let's say. Then show that Q1 equals Q2 equals 1. And that also Q3 equals S3. This is a simple but very important exercise. Okay, make sure you understood that situation. Exercise number 4, just some examples to fiddle around with Napier's rules. So solve for Q1, Q2, Q3, S1, S2 in a right triangle where we know that S3 is equal to 1, given these various initial configurations. And you can easily make up some values of your own and test your skill at applying Napier's rules. So in this video we've talked about right triangles and we've established important formulas for them. In our next video we're going to look at another type of special but important triangle, an isosceles triangle. Turns out that there's also some very nice and non-obvious relations between the various quadrants and spreads in an isosceles triangle. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.